All right, so get this.
Yeah.
Okay. Imagine, right? Imagine a computer can crunch numbers in 5 minutes, and those numbers would take the world's fastest supercomputer,
Mm.
like longer than the age of the universe to calculate. We're talking about that kind of power. With Google's new Willow chip,
Yeah.
you sent over a couple of sources, a blog post, and a scientific paper.
Mm-hmm.
Both are, diving deep into this leap in quantum computing. So, like, wherever you are in the tech world, right, whether you're deep in it or just curious about, like, what's next, we're going to break down, like, the key stuff from these sources, make sure it all makes sense, right?
Yeah, yeah.
And hopefully, just leave you thinking about the what-ifs of this whole quantum thing.
Absolutely. What's truly groundbreaking here is that Google has actually accomplished two major feats with Willow.
Okay.
They've managed to significantly reduce errors as they scale up the number of qubits. And they've showcased mind-blowing computational speed using something called the RCS benchmark.
Okay, stop right there. RCS benchmark. I'm guessing this isn't like your average speed test.
You're absolutely right. The RCS benchmark, or random circuit sampling, is considered the entry point for demonstrating what we call quantum supremacy.
Yeah.
It represents a class of problems that are insanely difficult for classical computers to solve, but they're relatively straightforward for quantum computers.
Gotcha.
And by surpassing classical computers on this benchmark, Willow is essentially signaling that quantum computers are starting to pull away in terms of computational power, and they will continue to just outperform them dramatically as they grow.
So it's kind of like a drag race
Exactly.
where the quantum car just left the classical car in the dust.
Exactly.
Okay, but let's talk numbers for a second, right?
Yeah.
That 5-minute calculation that would take a supercomputer longer than the universe is old.
Yeah.
I mean, that's almost impossible to even, like, fathom. Right.
It really is a staggering demonstration of the potential of quantum computing. And that calculation, by the way, is the same one used in the RCS benchmark.
Okay.
So it's not just some arbitrary task,
Right.
It's a problem specifically designed to show just how much faster quantum computers can be compared to their classical counterparts. And just to give you some perspective, the supercomputer would need 10 septillion years, that's a 1 with 25 zeros after it, to do what Willow did in under 5 minutes. It's mind-boggling, to say the least.
Okay, so that's seriously impressive.
Yeah.
But you also mentioned error reduction.
Yeah.
Now, I know a little bit about quantum computing, and one of the big things I've always heard is that these qubits are super fragile and prone to errors, right?
Yeah.
How did Google manage to crack that nut with Willow?
That's where it gets really interesting. Willow achieves something called below-threshold performance,
Okay.
meaning that the errors actually decrease as the number of qubits increases. And for decades, quantum error correction has been, like the holy grail of the field. Peter Shor first demonstrated the concept back in 1995.
Oh, wow.
But achieving it in practice has been a monumental challenge, and Willow appears to be one of the first real-world demonstrations of this theory in action.
So it's like they found a way to build this quantum system where, like, the more you add to it, the stronger and more stable it gets.
Yes.
That sounds almost counterintuitive.
It does, doesn't it? The key is something called the surface code.
Okay.
A specific type of quantum error correction code that's been considered particularly promising for large-scale quantum computers. It basically involves arranging the qubits in a 2D grid and using a clever scheme of measurements to detect and correct errors as they occur.
So it's like having this self-healing grid of qubits?
Yeah, yeah.
The bigger the grid, the better it can repair itself.
That's a great way to think about it.
That's pretty wild.
It is, and that's precisely what makes Willow's achievement so remarkable. But there's more. Remember I mentioned below-threshold performance? Well, one of the key ways they achieve this is by scaling up this surface code from distance 3 to distance 7, meaning they increase the size of that 2D grid.
Right.
And with each increase, they saw a significant reduction in the error rate.
Okay.
What this means is that for the first time, we have a quantum computer that can not only correct errors,
All right.
but also do so increasingly effectively as it grows.
Wow. Okay, that's a lot to unpack. So Willow's basically a quantum leap forward in error correction.
Yes.
But there was also something in the paper about beyond break-even. What's that all about?
It's another crucial aspect of Willow's performance. Beyond break-even signifies that the combined system of qubits working together with the sophisticated error correction, actually lasts longer than any individual qubit would on its own. And in their experiments, they found that their distance 7 logical qubit, think of this as a qubit that's been encoded using the surface code, had a lifetime of 291 microseconds, which was more than double the lifetime of its best individual physical qubit.
So it's like having a team that's way stronger than any of its individual players.
Exactly. It's a testament to the power of quantum error correction.
Yeah.
And the ability of the surface code to create a more robust and resilient quantum system.
Gotcha. This is all incredibly impressive, but I have to ask the million-dollar question here, right? What about real-world applications? Can this thing actually do anything useful beyond just proving that, like, quantum computers are getting faster and more reliable?
That's the million-dollar question, isn't it? And the truth is, it's complicated. While Willow has shown just incredible performance on those RCS benchmarks, which are specifically designed to, test a quantum computer's computational prowess, those benchmarks don't have any known practical applications yet.
Okay.
It's a bit like having a supersonic jet.
Yeah.
That can break the sound barrier, but you haven't figured out how to build an airport that can handle it.
So it's like a case of we built it, now what?
In a way, yes. We've proven that quantum computers can outperform classical computers on specific tasks. But the challenge now is to find those quantum airports, if you will,
Right.
those real-world problems where this technology can truly shine.
That's a great analogy.
Yeah.
So while we may not have those quantum airports built just yet, right?
Yeah.
The blog post does hint at like some exciting areas.
Absolutely.
Where this technology could eventually take off. They mentioned things like medicine, battery design, and new energy alternatives.
Absolutely, and that's what makes this whole field so tantalizing. The potential is immense, but we're still in the early stages of figuring out how to harness this power for real-world applications. But let's dive a bit deeper into how they actually achieved these results.
Yeah.
The scientific paper provides a much more detailed look at Willow's inner workings, and that's where things get really technical.
All right, lead the way. I'm ready to get into the nitty-gritty.
All right, so let's start by unpacking how they actually achieve that below-threshold performance with the surface code. Remember, we're talking about a 2D grid of qubits that's designed to, detect and correct errors. Well, they scaled this code up from what's called distance 3 to distance 7.
Right.
You can think of this as increasing the resolution of their error correction grid.
Okay.
And each time they scaled it up, from 3 to 5, then 5 to 7, they saw this remarkable halving of the error rate.
Okay, so each jump in distance led to a significant improvement in accuracy. That makes sense. But they also talked about some lingering error sources, right? Like they weren't entirely in the clear.
You're absolutely right. They identify a few key error sources that they had to investigate further. And one of the most intriguing was something called correlated errors.
Correlated?
Yes. These aren't your typical random errors.
Right
They
on.
happen in clusters, like little gangs of gremlins wreaking havoc on your qubits.
So it's like a domino effect then, where one error triggers a cascade of others.
That's a great way to put it. These correlated errors can come from various sources, including stray interactions between qubits, or something called leakage.
Leakage.
Right.
Sounds like something you'd want to avoid in any kind of computing, right?
Yeah.
What exactly does that mean in the quantum realm?
Well, in quantum computing, leakage happens when a qubit's state leaks out of its intended computational space.
Okay.
It's like having a bit that's supposed to be a 0 or a 1, but it somehow ends up in this weird, in-between state, messing everything up.
Okay, yeah, I see how that could be a problem. But I seem to recall they had a method for dealing with this leakage, right? Something with a rather cryptic acronym, DQLR.
You've got a sharp eye. DQLR stands for data qubit leakage removal. It's a technique they developed to actively combat leakage during the computation.
Right.
And their experiments showed that DQLR was essential for achieving good performance, especially as they scaled up to those larger surface code distances.
So DQLR is like their quantum leak-proof sealant, right?
Yeah.
Plugging those leaks as they spring up. Pretty ingenious.
Yes, yes.
But I'm curious, with all this talk about error correction, how quickly can they, decode these errors? Isn't there a risk that the decoding process itself could, become a bottleneck?
You've hit on a critical point. If the decoding process can't keep up with the speed of the quantum computation, it could negate all the benefits of error correction. That's why they dedicated a significant portion of the paper to discussing real-time decoding and the challenges involved. They needed a decoder that could rapidly interpret the measurement outcomes from the qubits and figure out what corrections needed to be made, like on the fly.
That sounds incredibly difficult. Like, how do you even begin to design a decoder that can operate at that speed?
Well, they had to get creative. They developed a real-time decoder that uses what's called a sparse blossom algorithm,
Okay.
which is specifically designed to handle the types of error patterns that are commonly seen in surface code decoding.
Hmm.
They also implemented a parallelization strategy, essentially dividing the decoding problem into smaller chunks that could be processed simultaneously.
So they basically gave their quantum decoder a turbo boost by breaking down the problem and tackling it from multiple angles at once.
Exactly. And the results are impressive. They managed to maintain that below-threshold performance even with this real-time decoder running.
Wow.
On average, their decoder had a latency of just 63 microseconds.
Okay. Which means it could keep pace with the incredibly fast operation of those superconducting qubits.
63 microseconds. That's lightning fast.
It is fast.
So, okay, they have this incredibly fast and accurate quantum chip.
Yeah.
They've figured out how to correct errors,
Uh-huh.
and they even have this real-time decoder that can keep up with the whole process.
Yes.
It's starting to feel like they've really, cracked the code for building a truly reliable quantum computer.
Yeah.
But I'm guessing there are still challenges ahead.
Yeah,
Wow.
you're right. It's not all smooth sailing from here.
Mm.
While Willow's performance is a giant leap forward, there are definitely hurdles to overcome before we see practical quantum computers solving real-world problems.
Okay, so what are the biggest roadblocks they've identified? Where do they go from here? One of the most pressing challenges is scaling up this technology while maintaining these low error rates. You know, they've shown they can achieve below-threshold performance with up to 105 qubits, which is already remarkable, but for many real-world applications, we'll need systems with thousands or even millions of qubits.
Yeah, I can imagine as they scale up, like, all sorts of new and unforeseen challenges might pop up. It's one thing to, control 100 qubits, right?
Right.
But millions, that sounds like a whole different ballgame.
Absolutely. Scaling up is not just about adding more qubits. It's about managing the complexity of the system as it grows. They also specifically mentioned needing to delve deeper into those correlated error bursts we discussed.
Right.
Those bursts appear to be the main obstacle to achieving even lower error rates, particularly in their repetition code experiments, which they use to, really stress test their system.
So even though they've made, remarkable progress with error correction, there's still this, lurking error floor
Yeah.
that they need to find a way to break through.
Right. But there's a silver lining here. Remember that exponential leverage of quantum error correction we talked about?
Yeah.
Even a small improvement in the physical error rates of the qubits could lead to massive gains in the overall performance of the logical qubit.
So even, incremental progress on the hardware side could have a huge impact on the system's, overall capability.
Exactly.
It sounds like there's a lot of optimism about the future of this technology, despite the remaining challenges.
Absolutely. The progress made with Willow is a clear sign that we're heading in the right direction. Achieving below-threshold performance with the surface code and a real-time decoder is a major milestone on the path to building fault-tolerant quantum computers.
I'm definitely feeling inspired. It seems like we're on the verge of something truly groundbreaking.
Yeah.
But before we get too carried away, dreaming about the future, I think it's important to touch on one final point that the paper raised.
You're talking about the limitations of their current testing methods, right?
Mm-hmm. Exactly. They were very upfront about the fact that while their repetition code experiments allowed them to hunt for errors with incredible sensitivity, those codes aren't directly applicable to fault-tolerant quantum computation.
That's a good observation. They essentially use those long repetition codes as a kind of stress test,
Okay.
pushing their system to its limits to see where those pesky correlated error bursts would show up. This was a valuable exercise for understanding the underlying error mechanisms at play, but it doesn't necessarily tell us how those same errors will behave in a more complex system using the surface code.
So they've identified some like potential weaknesses in their system.
Yeah.
But they still need to develop new testing methods to see how those weaknesses will affect their ability to like perform complex computations with error correction.
Precisely. And they acknowledge that there's still a lot of work to do in terms of developing those new testing methods and figuring out how to scale up their error correction techniques to even larger systems.
All right, so we've covered a lot of ground here. We've explored Willow's impressive performance,
Yes.
the breakthroughs in error correction, the intricacies of real-time decoding,
Yeah,
and even the challenges that still lie ahead.
absolutely. It's been a fascinating deep dive.
Yeah.
From the theoretical foundations of quantum error correction to the practical details of, implementing the surface code and achieving those remarkable error suppression rates. There's so much to absorb and contemplate. But let's shift gears for a moment. We've talked a lot about the technical nuts and bolts.
Right.
But I'm curious about the broader implications of Willow's achievements. Where do you see this technology heading in the next few years? What kind of impact could it have on our lives?
Now we're getting to the really exciting stuff. Let's talk about the potential of this technology. Okay, so we're back for like the final stretch of our deep dive into Google's Willow chip. And you know what? I'm so fascinated by those correlated error bursts we talked about earlier. They're like these like tiny quantum earthquakes just like shaking up the whole system.
Yeah, they are quite a mystery. Remember how they were much less frequent than those high-energy impact events from earlier experiments? Yet they were still like causing trouble, especially as Google pushed those repetition codes further.
Right, yeah. It's like they found a new species of quantum gremlin,
Yes.
and they're still figuring out how to deal with them.
Exactly. And the fact that they ruled out those, common culprits like cosmic rays
Right.
and background radiation makes it even more intriguing. They even suggested that the source might be the, materials of the chip itself.
Yeah, they had a hunch that like microscopic defects in the superconducting materials might be like trapping energy and then releasing it in these bursts, leading to those correlated errors.
Right. It's a reminder that even at the forefront of technology, we're still wrestling with the imperfections of the physical world, especially when you're working with something as delicate as quantum information.
So building a quantum computer is like kind of like playing Jenga with the universe.
Yeah.
One wrong move and the whole thing could just come crashing down.
That's a vivid image. But here's what I find particularly interesting. They discovered that these error bursts have a distinct pattern, They aren't just randomly scattered across the chip. They tend to cluster in certain areas.
Oh, yeah. Yeah, I remember those heat maps in the paper. It was like looking at like a weather map of quantum errors with storm clouds of correlated errors forming in specific zones.
That's a great way to put it. And that spatial pattern offers a vital clue for mitigating these errors. Okay.
If they can pinpoint the cause of these clusters, they might be able to design the chip in a way to minimize those problem areas.
So they need to become quantum meteorologists, right?
Yes.
Predicting and preventing those error storms.
Precisely. And, this kind of detailed error analysis is incredibly valuable. It allows them to, move beyond simply measuring the overall error rate.
Right.
And begin to really understand the root causes.
Yeah.
Which is crucial for developing more effective strategies to combat them.
So we've explored the depths of those correlated error bursts, but I want to zoom out now.
Okay.
Where does Willow fit in the grand scheme of quantum computing?
From my perspective, Willow represents a significant stride toward what's called fault-tolerant quantum computing.
Okay.
Which has been the ultimate goal of the field for decades.
Now, remind me, what exactly does fault-tolerant mean in this context? It's the idea of building a quantum computer that can, reliably perform these complex calculations even when errors inevitably occur. It's a monumental challenge, like trying to build a house of cards in a windstorm.
Sounds like a recipe for disaster. But are they saying that, they've achieved this with Willow?
Not quite.
No.
But they've demonstrated that one of the key building blocks for fault-tolerant quantum computing, that below-threshold performance with the surface code, is within reach.
Right.
And it's a massive accomplishment.
So they've essentially shown that the theoretical foundation for building a reliable quantum computer is solid, right?
Yeah, yeah.
Now it's a matter of engineering and scaling up.
Precisely. And the fact that they've achieved this with superconducting qubits, which is, one of the leading technologies in the field,
Right.
is even more significant. It suggests that this approach has the potential to, really lead us to these large-scale fault-tolerant quantum computers.
It's all very exciting, but as we've discussed, there's more work to be done.
Absolutely.
What are the major obstacles they need to overcome to turn this dream of a fault-tolerant quantum computer into reality?
Well, as we've touched on, those correlated error bursts are a major hurdle.
Yeah.
They need to find ways to either eliminate them altogether or develop error correction codes that are, more robust to these bursts.
So they either need to find a way to stop those quantum earthquakes,
Yeah.
or build a quantum computer that can withstand them.
Exactly. They also need to continue improving the coherence of their qubits, which basically means extending the time they can, maintain their quantum state.
Okay.
The longer the coherence time, the more intricate calculations they can perform.
So it's extending the lifespan of those delicate quantum states, right?
Yeah.
Giving them more time to work their magic before they fade away.
That's a good way to think about it. And of course, they need to keep scaling up the technology. They've shown promising results with 105 qubits, but we'll need systems with, thousands, millions, or even billions of qubits for many practical applications.
I imagine that scaling up isn't just a matter of adding more qubits, right?
Yeah.
It's about managing the complexity of the system as a whole.
Yes.
Like a giant quantum orchestra where every qubit needs to play in perfect harmony.
That's a fantastic analogy. It captures the essence of what makes quantum computing both fascinating and challenging.
Yeah.
It's this delicate dance between the quantum and the classical worlds, and it requires this, deep understanding of both to make it work.
Well, I think we've reached the end of our quantum journey for today. We've delved into the intricate details of Google's Willow chip, from its groundbreaking performance to the persistent challenges of, error correction.
Yeah.
And the alluring potential of, fault-tolerant quantum computing.
It's been a thrilling deep dive. And I hope you've gained a, clearer understanding of the incredible strides being made in this field,
Yeah,
as well as the hurdles that remain.
absolutely. It's clear we're still in the early stages of quantum computing,
Yes.
but the pace of innovation is rapidly accelerating.
It is, yeah.
Who knows? Maybe one day we'll look back at Willow as the catalyst that sparked a quantum revolution, transforming our world in ways we can only imagine today.
I, for one, am incredibly excited to see what the future holds.
Me too. Me too. Well, thanks for joining us on this deep dive into the world of quantum computing. We'll be back next time with another fascinating exploration of cutting edge science and technology. Until then, keep asking those big questions.
Yeah.
And never stop exploring the wonders of the universe.